And we're back for part 3 of the least squares approximation. Why do we call this the least squares approximation method? Well, the reason is when we find the error, it's the magnitude of the error vector, which using the Euclidean inner product is the sum of the squares of the components of the error vector. And so to make the error the smallest, we're trying to make the sum of the squares the least. So the squares of the components, we want those to be the least. Therefore, the least squares gives us the minimum error and therefore the closest vector. So let's write that down here. So we're trying to minimize error, which is equal to the magnitude of the error vector, which is equal to the square root of the first component 1 squared plus E2 squared plus E3 squared plus yada yada. And we could go all the way out to the nth vector component squared. So we're trying to minimize the error, and that's the least sum of the squares of the components. Okay. All right. Now, a little bit earlier when we were solving this normal system, we set up the normal system, and then we solved him. We did it through RREF. So we made an augmented matrix and RREF that to find our x1 and our x2. Okay. Now, let's just take a second here. We said that A transpose AX equals A transpose B. Now, here's something cool. If the columns of A are linearly independent, then the matrix A transpose A will be invertible. In fact, that's an if and only if theorem. So if our columns of our original matrix A are linearly independent, then there exists an A transpose A inverse matrix that I can multiply onto the left of both sides here. And since this is A transpose A and A transpose A inverse, that will give me the identity times the X matrix, which of course is just the X vector. So the X vector is A transpose A quantity inverse times A transpose times B. Okay. Now, let's go ahead and use our calculator to double check our work. So if I type A transpose A parentheses inverse times A transpose times the B vector in the calculator, I should find out that the X vector, the least squares solution, is -0.8 and 1, which matches up perfectly with what we did by RREF. So X is equal to X vector is -0.8 and 1. And once again, these guys tell us the coefficients to make the vector that's the closest. So -0.8 times vector column vector 1 plus 1 times column vector 2. Whoops, 1, 2, 3. And that will give me the vector that's the closest to the desired vector 3, 3, 3. Okay. Now, this method will work if and only if the columns of A are linearly independent. Okay. If the columns of A are not linearly independent, they are linearly dependent, then this matrix is not invertible, and you have to go with the RREF method. But in that case, you actually have not one solution, but infinitely many solutions. So you'll have a parameter or more, but at least one parameter. And therefore, any one of those is the best answer. Okay, so hopefully that's made sense. Okay. Let's go ahead and work on another problem. Let's give another one a try here just to practice. So let's take this system right here. -x1 plus 2x2 equals -2. -2x1 minus 2x2 equals 1. x1 plus 4x2 equals -1. And let's find the least squares solution. Well, first off, let's create a visual of this so we can see what's going on. Okay, I've just created or modified my Geogebra here. So you can see that I've redrawn the vectors 1 and vector 2. So we've got a new plane. And how did I find the equation of that plane? Well, I did the cross product of these two vectors, and then I factored out the common term, and then just used those as the coefficients like we learned in chapter 3. So we're trying to make this purple vector to, negative 2, 1, negative 1, but you'll notice that he's not in the plane. So if I try to solve that system as is, I'll get an inconsistency. So we need to try to find the W vector in the plane that's the closest. And to do that, I need to find out the X vector, which tells me how much of the first vector plus how much of the second vector, to find the vector that's the shadow of this guy, the orthogonal projection, onto this blue plane, or sorry, yeah, this aqua kind of plane here. So let's set up the system and then have you work through it, and we'll double check here with you in just a second. Okay, so let's set this up. So our A matrix is going to be negative 1, 2, negative 2, negative 2, 1, 4. Our B matrix is negative 2, 1, negative 1. Okay, and so our normal system is going to be A transpose A times X equals A transpose B. And I'm going to run those on my calculator really fast. I get 6, 6, 6, 24 times x1, x2, because that's the x vector, equals A transpose B. I get negative 1, negative 10. And I have a couple of choices here. I can either RREF this, since the column vectors of my original A matrix are linearly independent. They are not scalar multiples of each other, which is the easy way to check if you only have two vectors. And so we can then find the solution for X here, either using the inverse of this matrix or augmenting and RREF. Okay. So when we do this, I find out that the X vector, in other words, x1, x2, is 1/3 and negative 1/2. And so let's use that to find out who the W vector is that's in the space that we can make. And as we've seen, that W vector is A times the X vector. So let's punch that in on our calculator. When I do that, I get negative 4/3, 1/3, whoops, I guess I should have made that longer, and negative 5/3, which is sort of close to the negative 2, 1, and negative 1 that I wanted to. And so we want to find the least square solution. We've done that. We want to find the vector that's closest to B. That's W, which again is the orthogonal projection of the B vector onto the W space, the column space. And we need to find the error. So the error would be the magnitude of the difference between W and B. And so the error vector we would get, if I do W vector minus the B vector, so negative 4/3 minus a negative 2 is 2/3. 1/3 minus 1 would be negative 2/3, and negative 5/3 minus a negative 1 would be negative 2/3. And so the error then would be the magnitude of that. So the square root of 2/3 squared plus negative 2/3 squared plus negative 2/3 squared. So that's 4/9 times by 3, which would be 4/3. So that would be the square root of 4/3, or 2 over the square root of 3. And we would then find out that that error then, or the length of the error vector would be to 4 decimal places, 1.1547. Okay. All right. So again, remember who all the moving parts are. X is the least square solution. It's the answer that's the closest, or well, it's the coefficients that get us to the closest to the original vector we wanted to make. Okay. All right. So that's 6.4 least square solution.